Welcome everybody. In this video we're going to expand on what we did in the last video and investigate the consequences of when infectious people can only infect others who are still susceptible. One of the consequences that we can investigate is how social distancing can flatten the curve. So that's what we'll do next. The model that we're going to investigate is pretty much the same as the ones that we've talked about before. Really the only new thing is this lowercase s, which stands for the fraction of susceptible people. So this guy here, remember the thing that goes on the arrow is the infection rate, which we're also going to call Ri, and it has three components. It has Ki, Ni, and S. And the thing is that Ki is the infection rate constant. It has units of 1 over days. The next thing is Ni. It's the number infectious, and it has units of just a number, like 1. And then the last thing, this lowercase s, right, this lowercase s, it has units of also just a number because it's a fraction. It's the fraction of the model population that is still susceptible to the virus. Alright, so that's pretty much the model in a nutshell. And what I'd like to do next is to show you the website where you can get the chapter that we're talking about. So if you go to circle4.com/biophysics, which is listed in the PowerPoint back here. Let's go back there. Right, so it's listed here in the PowerPoint. If you go there, there are 3 sample chapters. So if you click on that, it'll give you the list of all the chapters. The one that we're working on right now is Chapter 12, COVID-19 and Epidemiology. I'm currently up to version 1.7, which is sections 12.1 and 12.2. And yes, I'm still working on it. There should be about 6 sections, or maybe more, but probably 6. Alright, so if you click on that link, you'll get the PDF, and I have that here already loaded into my favorite PDF reader. And here's that same diagram that we were talking about. I need my highlighter. There it goes. Right, this is the same model we were just talking about. Here's the rate, and here's the formula for it, and it has a number 12.8, and that's going to be important. Here we have the definition of what lowercase s is. It's the number susceptible divided by the total number of the population. And that total number is just the sum of the number susceptible and the number infectious. Alright, so, and one of the other things that I mention in the chapter, as you go through it, you'll see I refer to this marble game, which is what the whole book is about. And if you click on this link, it'll actually take you to this web page, which I have kind of preloaded. And what it is, you'll see there's a whole bunch of little marbles, molecules jiggling around. They're in solution, right? So all the black space is actually meant to be water molecules, and the ones that you can see, there's 50 of them, are being jiggled around by the water molecules. So how does that relate to our epidemiological model? Well, the idea is that if you zoom in on this thing, too far. If you zoom in on this thing, you can see these guys are all jiggling around, and if you want to zoom in more, this is a 3-dimensional model, so you can actually look inside and then rotate, maybe, there we go, rotate. And the idea is that if 2 of these guys randomly bump into each other and get close enough, if one of them's infected and the other one is not, one can infect the other. And so the idea is that the rate of infection caused by one infectious person depends on the fraction of people that they bump into that are infectious. And that's actually what's included in this definition of S, right? So S is just the fraction of susceptible people over the total. Alright. And then there's some things that kind of explain how this makes sense. S is this fraction we just talked about, but at the very beginning, when basically nobody's been infected, they're all susceptible. So that ns is basically the same as n, and n over n is 1. Right? So if you go back and have a look at this equation, if s is 1, this ends up being the same as the equation that we used in the previous model for exponential growth. So it reduces to that model at early times. But at later times it does something different. So question 1211 says you have to go through and do substitute, and it's a show that problem, which is an algebra problem. The idea of the algebra problem isn't to torture you. The reason for having algebra problems in here is so that you go through and make sure you understand where this formula comes from. It's really just based on this equation that we've already talked about. So I'm going to assume that you've already done that. And here are the equations for the algorithm that we're going to use, and I guess I can quickly show you the algorithm. So I'm going to cheat and show you the answer. Where are we? Oh, I need that back. And here's the model answer. So, right, this is your cheat sheet if you're doing this for homework. So here are the parameters with the units, right? The time step is going to be 1. The infection rate constant is 0.3. The initial number infected is just 1. The variables, time has units of days. The infection rate has units of per day. And NI and S, the number of infected and susceptible, are just numbers, so they don't need units. In step 0, we set time to be 0, right? The new just means the value of time in this step. The value of the number infectious is just the number that we want to start with, which was the number we just talked about, 1. And there's a formula for calculating the new number who are susceptible, and it's just the total number minus the number infectious, right? So these two things have to add up to n, so this formula is just a consequence of that. In step 1, we have the new time is the old time plus the change in time. The new rate of infection is Ki times Ni old times Ns old divided by the total population, right? This thing is just the lowercase s that we talked about. And then the new number infected is the old number infected plus the infection rate, the one that we just calculated, times the time step, delta t. Alright, so this should seem fairly familiar from what we were talking about last time. The main difference is that the infection rate now has the number susceptible and is divided by n. And then the last thing that's also new, it's actually the same as this, right? If you notice, these two formulas are the same. It says that the number susceptible in step 1 is equal to the total number in the population, which is 1,000, minus the new number, right, this guy that we just calculated, the new number infectious. And then there are unit checks. I'm a big fan of making sure that people always check their units, because you can get in trouble in science if you don't pay attention to them. So the infection rate, it's given by this formula. That's basically the same formula as this, but without all the stars and news and olds. And Ki is the only thing that has units, and the other things all have units of 1. So because this is the only thing with units, the whole thing ends up being in units of per day. Ri should have units of per day, so that's good. Same thing here for the new number infectious is the old number infectious times the rate times delta t, and this thing has units of 1, right? It's the same as a number. This thing has units of 1 over days, and this thing has units of days. So these two things multiplied together end up giving us something that doesn't have units, right? It's dimensionless. And then here's the finite, the output table. You should check that you actually get this when you do it by hand. So that's part of the procedure of doing the problem. Back in the chapter, where are we? There it goes. Chapter 2. Alright, so the next thing we want to do is, I just have to change the thing, let's do that. And so we have, it says open the pre-formatted spreadsheet. So if I click on this, it should open it. And I have to go to the browser just to say OK. So if I click OK, it shows me that Excel is loading. Alright, so here's the Excel thing. And the algorithm that I had just shown you tells you how to fill this in. So I have got it on a piece of paper next to me, so I'm going to use it to fill this in. And I need to enable editing. And then the next thing I need to do is just double check that I understand what's going on. So N here is the total number of the population. We're only considering 1,000 people. The time step is 1 day. KI is 0.3. So one infectious person infects 0.3 people per day. Right, so it takes just over 3 days for them to infect a person on average. And N0 is the initial number infected, and that's 1. Alright, the parameters here, so this column is time, and it has units of days. This column is the rate of infection, and it has units of per day. And then these two columns are for the number infectious and the number susceptible. Alright, so using our formula that we had, it was equals and then KI, and remember I have to hit F4 to get the dollars, times NI old, which is that guy, times NS old, which is that guy, divided by N, and again that's a parameter, so I have to hit F4, and if you're on a Mac you have to put the dollar signs in by hand, hit enter, and so that calculates the rate. So it says on day 1 0.2997 people get infected. Alright, then we have to calculate the new number infected, and remember that was equal to the old number infected plus the rate times the time step. And again, that's a parameter, so I need to do F4 to get the $A, $5. If I hit enter, that calculates the new number infectious. And here, well, the formula, and I didn't show you this before, the formula here is actually doing the formula from the algorithm, and that should be the same one for step 2. So I can just go from here, if I just move over to that blob, see it changes to a closed cross, and then I can drag down one. And so now we've inputted all 3 steps. And one of the cool things about Excel is that if you highlight, so if I click in the middle of this cell and then left click drag across, I can highlight them. If I move to that blob on the bottom corner, get that closed cross, and left double click, it fills in the spreadsheet down to the bottom, which I go out to day 47, and it actually shows you the curve. So this shows that the new infection rate starts to increase exponentially, and then eventually what happens is the population starts to become mostly, or at least somewhat, infected, and that slows down the rate of infection, and then eventually it decreases because we've run out of people to infect. So that's what you're supposed to do for this to input the model. But we need to talk about one more thing. It says, as always, you need to reduce, let's do this, as always, you need to reduce the time step and add enough steps so that the curves visually reach steady state. So the reducing of the time, again, because this is a stiff equation just like the one we did in the previous video, what we need to do is, where are we? Excel, there it goes. We need to check this. So I can see from this model that it's going out to about 50 days. So what I'm going to do is left double click on there, and it should pop up there we go, pop up the format axis thing, and I'm going to just delete the 0 and then hit enter, and it tricks Excel into thinking I entered 50, and it makes it a fixed axis. On a PC it looks like this. I can't remember exactly how it looks on a Mac. It's a little different. So that fixes that axis, and I want to do the same thing for this graph. So I'm just going to, delete the 0 and hit enter. And so both of those are now fixed. So what I'm going to do next is I'm going to add a whole bunch of rows, and it turns out we're going to need quite a lot, just like last time, because this is a very tricky equation from a numerical point of view. You need a lot of steps, a lot more than you would expect. So I'm going to do 5003, and it won't make any difference right now, but went too far. Always go too far. Alright, so I want 5003. There we go, 5003. So they'll populate. Alright, so if I go back, the graph won't have changed much, but let me get rid of that. Alright, so if I change the time step, right, so we're currently doing a whole day, which you would think, it doesn't look like it's a lot on here. There are 50 days across here, but if I change it to half a day, have a look at this peak and watch it as I hit enter. Right, so look here. Can you see that it actually moved that way? It got smoother as well, but so that's not good, right? We don't really want our model to depend on what the value of the time step is. So let me change it to 0.1, right? We don't want it to change. Oh, but it did, so that's not good. Let's make it half as big again, 0.05. And you'll see it moved just a smidge. If I make it to 0.02, just a tiny fraction, and then if I make it 0.01, basically it stops moving. So that's good. So once again, we need to have the time step be 1/100th of a day to make this thing work properly, which is really quite surprisingly small. Anywho, okay, so that answers our question, I think. Let me go back and check. Let me do, what number are we doing? We're doing 1212. So do file, save as. It's always good to save these things. I want it to go, yes, that's where I'm working. So I'm going to change that to be BPM question 1212A. Let's do that. And I'll keep the description because it's good. And get rid of the -5, which we don't need. Alright, let's do that, save, and then let's just double check we were actually doing question 12. Yes, we were, and we were doing part A. So there you go. Oh, and the hint, I kind of buried the hint. Here it is. It says it goes out to 503 for a good reason. So that was my hint about maybe you want to use 5003 steps. Then part B is you are expected to figure out why the curve for RI has a peak, whereas NI always increases. So let's just go back to Excel and just look at that, right? So the idea here is that this curve has a peak, but this curve, the blue curve down here, for the number infectious, always increases. So if you think about it and you understand the model, you should be able to answer that question. I don't think it's too hard. Okay. Alright, so what do I need to do? Oh, go back to the questions. Alright, social distancing. So this is the payoff for this model, is that you can actually investigate the effect of social distancing. So the question 13, what it says to do is to change Ki to be 1/2 of the original, right? So originally it's 0.3, and it says change it to half the value and see what happens. Alright, oh, and there's a hint. I'll tell you the hint this time before we do it, right? You can use the longest time step. So that's a bit of a hint. Let's see how that works. Alright, oh, and I always forget 13. So we're up to 13. So what I'm going to do, I've already saved this guy, so I'm going to do File, Save As, because we're going to do 13 now. I want to save it as question 13. It's always good to save your work. Alright, so what we're going to do now is it said change the Ki constant from 0.3, which is what it currently is, to 0.15. So the idea of social distancing, and it's explained in the chapter at some length, is that what social distancing does is it lowers the rate of infection because people are not interacting with other people as much. So what we're going to do now is just assume that we've done some kind of social distancing, and basically you're interacting with half the number of people that you normally would that you don't know. And so we're going to say that will change the infection rate constant from 0.3 to 0.15. So if I enter that, let's see what happens to the graph, right? So I always like to look over at the graph while I'm hitting enter, so you should do that. And you'll see it moves the graph over to the right. It's like, oh, okay. And I'm going to make a guess for how much it moves it across, because, oh, okay. So why is it stopping here? Well, part of the reason for that is that because we've got such a tiny time step, even though we've got 5,000 steps, we're only going out to 50 days. So I'm going to increase the time step just like the hint said. And if I do backspace and go 2, right, double it, nothing happened. Why not? I forgot. I had maximized this guy and made it have a maximum of 50, so I need to change that. I'm going to change it to double the amount of time. And now, and do the same thing down here, make that 100 as well. So, alright, hit enter. And now if I get rid of the format axis window, alright, so we have got for our new infection rate, you can see it has pretty much the same shape, but now it's going out to 100 days instead of 50, which it was before. But one of the things you might not have noticed was that the vertical axis also changed. Before, and you can go back in the video and check, it went up to I think 80, and now it's going only up to 40. So the peak has been lowered, right? So this is actually doing what people have been talking about for a long time. You can flatten the curve by lowering the infection rate constant, and this very simple model actually illustrates that. Let's see what happens if we lower it even further. So I think that's what the question says. Yes, it says here it says lower it to 1/4 of the original and see what happens there. Well, let's see. We might even be able to guess what's going to happen, but let's just put the number in and see what happens. That's one of the fun things about doing Excel for this. So it's 0.075. I think that was right. Oh, and we get the same issue that we had last time, so now we know what to do. Let's double this to 200, and we'll double that one to 200 as well. Not 300, 200. And hit enter. And then, oh, the other thing we need to do is we need to double the time step so that we get our 5,000 steps actually get to the end of the simulation that we're running. It's not a simulation, it's a numerical model. Technical difference. Like, shame on me for saying misspeaking. Anyway, if you read chapter 3, you'll understand why. Alright. So once again, we doubled the time, so we're now going out to 200 days, and the curve is still kind of the same shape, but again, notice we were at 40 before, and now we're at 20, so it's lowered the curve, flattened the curve, right? That's what they usually say, flatten the curve by a factor of 2 again. So if you have only 1/4 the number of social physical interactions with people, then you can actually flatten the curve by a factor of 4, which is pretty cool. Alright, so, oh, and we should save that as file, save as, I think this is part B, so let me save it as part B, 13B, Yes. Go back and just double check that I was doing the right thing. Yes, so that's that. And then briefly describe how decreasing the infection rate constant. Okay, so what this is doing is it's actually the question, right? So most of the rest of the book I'm not going to do videos on, but what this question is it's designed to try to get you to realize what I was just talking about. And then, so D, so this is actually something that if you haven't had a look through the chapter, you might not realize. So the chapter begins with, let's go back to the beginning. It has this picture of social distancing, right? So they had this picture that I found on the web. It was by Nancy Goff, and it was published on Medium in March 10th of 2020. Anyway, so this was one of the motivating things for this whole chapter was, can you understand why social distancing will lower the curve, flatten the curve? All right, so what we've actually discovered is that if we halve the infection rate constant, we can go from a peak that's this big to one that's half as big. And in fact, if you've already looked at the chapter, you'll know what I'm going to get to. There's a graph. I need to find it way down the bottom here. Oh, there it goes. All right. Oh, and I kind of jumped over something, but I'll come back to it. So this is actually curves, and I used a different format, which I don't expect my students to do, but it's kind of cool to make it look like the published graph. So this is the one that we were just talking about, and with 0.3 is the 0.3, right? So 0.3 as the infection rate constant, 0.3 per day, and the second one is when it's halved. So these are the two curves, and it shows you what the effect is. The only tricky thing about this was because of the area graph, I didn't want to use 5,000 points because it would mess it up. So I did it with just 1 day, which, as I say here, is too big. All right, so anywho, so that's what that's about. The next part of the exercise is to change the number infectious. Now it's pretty straightforward, so I'm not going to go through that in this video. I'll leave that as an exercise. One of the things I do get you to do is to actually use the total number of the US population, which is a big number, right? It's 3.3 times 10 to the 8th, which you can enter. So this is the reminder, because I've talked about it before. 3 times 10 to the 8th, 3.3 times 10 to the 8th, you can enter it in Excel, and this is the correct way to do it. Enter it as 3.3 E8, and Excel will recognize that as 330 million. All right. So, and then these are discussion questions that I'm not going to talk about now. You can go through and see if you can figure out what the right answers are. And then this next question is actually kind of important, and it says, briefly describe what you think the main limitations of this finite population model, the one that we've just been doing, are. For me, this is actually one of the most important parts of the book, is trying to teach folks how to think about how models work and how to make them better. And then question 17 is one that I haven't actually done. I think I might now know what the answer is, but when I wrote it I had no idea if it was even possible, but now I think it might be. Anyway, and then the last part, which I do want to talk about a little bit. I'm not going to talk about this. If you haven't done chapter 8, it'll kind of freak you out, so don't worry about it. This is just saying that you can figure out what the total number infected are. One of the things I wanted to talk about is something, this is motivation for the next section, is I was really quite surprised a week or so ago. I was watching TV and I saw a journalist who I actually think is a pretty smart person, and they said this quote, right, which is, okay, so here's the quote, and it basically says, if I can paraphrase, that you're not reducing the number of people who get sick. What you're doing is just spreading out the infection over a longer period of time so that the healthcare system can handle it. And that's exactly what this finite population model predicts. But in the next section, we're going to talk about this SIR model. And what it does is it shows that that prediction that I heard on TV, and I've heard from many people actually, is just not correct. It's really not correct. This model actually shows that social distancing can not only lower the infection rate, but it can reduce the cumulative total number of people who get infected. And if you did it early enough, you could even prevent the outbreak from occurring at all. Which sounds like a good idea, but unfortunately the cat's out of the bag here in America. So anyway, that's what we're going to talk about in the next video. So stay tuned, and I'll be posting that soon. So just a reminder, this is a link to the project that I've been working on, and it's at circle4.com/biophysics. Go to the top of the page and you'll see a link to the free chapters and links to the other videos in this series.